Advanced GraphRAG and Knowledge Agents, let's dig in. In Module 1 we proved why graphs beat flat vector search on multi-hop, scattered, and global questions. Revisit it if you need a refresher. But we deliberately skipped the hard part. How does a pile of messy documents actually become that graph? That's the whole job today. Graph construction is the craft of turning unstructured text into a queryable topological network. And here's the twist that makes this module interesting: there isn't one way to do it. Two major paradigms exist, with almost opposite strengths and weaknesses. Pick wrong and you'll feel it for the life of your system. So here's the fork in the road. Path 1 builds the graph fact by fact as precise atomic triples. Path 2 zooms out and groups the graph into communities. One is a microscope, the other is a map. Watch them branch, we'll walk down each path in turn. Path 1, triple-based knowledge graphs. We hand each chunk of text to an instruction-tuned language model and ask it to do open information extraction. Pull out facts as subject, predicate, object. Open just means we don't force a fixed vocabulary up front. The model extracts whatever relationships it finds. Look at one triple up close. Steve Jobs co-founded Apple. That single subject-predicate-object becomes two nodes and one labeled edge, the smallest possible unit of a knowledge graph. The triple is the atom. String millions of them together and you've got a graph. Notice these are the same nodes, edges, and properties we met in Module 1, now being manufactured. Triples have a beautiful property: they are precise, atomic, and auditable. Every edge traces back to the exact sentence that produced it. For a doctor, a lawyer, or an auditor, that traceability is gold. You can always point at the source and say, that's where this fact came from. No hand-wavings. But triples have a dark side. Extraction runs as a pipeline: first entities, then relations, then coreference. If the model misreads an entity early on, that mistake doesn't stay put. It poisons every downstream triple that depends on it. One bad node at the top cascades into a whole region of wrong edges. Garbage in, garbage propagated. The second cost is your wallet. Triple extraction means calling a language model on every chunk across the entire corpus at indexing time. For a big document set, that's a mountain of tokens before you've answered a single question. Precise, yes, but cheap, definitely not. Now path 2, and it's a genuine change of altitude. Instead of obsessing over individual facts, we step way back and ask, which entities clump together? We group the dense graph into communities, clusters that are far more connected inside than outside. Think of a party. The tight friend group huddled in the corner is a community. What makes a clustering good? A single number called modularity, written Q. Plain English, Q rewards clusters with more internal edges than you'd expect by random chance, and penalizes links that get cut between clusters. High Q means crisp, well-separated communities. The clustering algorithm's only job is to push Q as high as it can. The algorithm that maximizes Q in practice is Leiden. It's a refinement of an older method called Louvain. Louvain was fast but had an embarrassing bug. It could hand you communities that were internally disconnected, a friend group where two members never actually met. Leiden guarantees every community is well connected, and it converges faster too. Here's the part that makes Leiden perfect for GraphRAG: it works in levels. First, it finds small local communities. Then it collapses each one into a single supernode and clusters again. Repeat and you get a hierarchy. Level 0 is fine-grained neighborhoods, higher levels are broad themes. One run, many resolutions of the same corpus. Now the payoffs. Once we have communities, we have the language model pre-write a short summary for each one, a community report, just once ahead of time. Stack those reports up, and you've got a global summary map of the entire corpus. When someone asks a broad question, you read summaries instead of dumping every raw document, so you never blow the context window. Communities aren't free either. They give you cheap, scalable global summaries, but in exchange they blur fine detail. A summary is a summary, it smooths over the specifics. And building that multi-level hierarchy costs more tokens up front than flat triples. Every paradigm bills you somewhere. Let's lock in the mental model. Triples are a microscope, precise, atomic, auditable, perfect for a specific factual question. Communities are a map, global, scalable, perfect for what are the themes questions. They are not rivals. Most production systems build both and let the question pick the right lens. Now a knob that sits underneath both paradigms, straight from the Zhang survey. You can extract schema-free, let the model invent any entity and relation type it likes, or schema-constrained, only allow types from a list you defined. Schema-free gives high coverage, but noisy graphs full of synonyms and junk edges. Constrained trades a little recall for a lot of precision. Picture a gate. Candidate triples line up, some match your allowed types, some don't. A strict schema gate lets the legal ones through and drops everything off schema on the floor. Less coverage, sure, but the graph that survives is clean, typed, and trustworthy. In a medical setting, that trade is a no-brainer. To enforce a schema, you need somewhere to hang it, and that's a property graph. Back in Module 1, nodes and edges could carry properties. Here those properties become first-class citizens of the schema. A drug node carries dosage. A trial edge carries phase and date and confidence. The property graph is the rigid backbone the whole schema rests on. One more idea before the lab from the KAG paper. Mutual indexing means every graph node keeps a link back to the exact text chunk it came from. So you reason over clean structure, then drop back to the raw prose for evidence, best of both worlds. KAG reported nearly 20% better F1 on one multi-hop benchmark and 33% on another, and Ant Group deployed it for eHealth and eGovernment Q&A. That's exactly why our lab targets medicine. Time for the lab. Our mission, schema-induce a property graph over a medical clinical trial corpus, then build communities on top of it. High stakes means we want maximum precision and minimum noise. Two halves: first build the schema-typed graph, then create the communities. Before we touch code, let's meet the two tools doing the heavy lifting. First tool, LlamaIndex. In plain English, it's an orchestration framework that connects your data to language models. It handles loading documents, chunking, embedding, and building indexes so you don't wire all that plumbing by hand. For us, the headline feature is its property graph stack. It can read documents and extract a typed graph for you with a schema you control. 3 objects do the work. PropertyGraphIndex is the builder and brain. Its from documents method runs the whole pipeline. SchemaLLMPathExtractor is the schema gate. You give it the allowed entity types, allowed relation types, a validation map of which relations are legal between which entities, and a strict flag. And Neo4j property graph store is where the finished graph actually lives. Remember these 3, they're about to show up in code. Second tool, Neo4j. It's the world's most popular graph database. Why a graph database instead of a regular table store? Because relationships are first class, stored, indexed, and traversed natively, exactly the topological power we argued for in Module 1. In a relational database, a multi-hop join gets exponentially painful. In Neo4j, walking edges is the native move. Neo4j's building blocks, nodes with labels, relationships with types and properties on both. You query it in Cypher. We met a tiny taste in Module 1, using its friendly pattern syntax with parentheses for nodes and arrows for relationships. And bolted on top is GDS, the graph data science library which ships heavy-duty algorithms. The one we need is GDS.Leiden, and it's how we'll create our communities. Now we build. Step 1 of the schema is just lists. We declare our allowed entity types, things like drug, disease, trial, outcome, and our allowed relation types, treats, has, phase, measures. These 2 lists are the vocabulary the extractor is allowed to use, and nothing else. Defining them is the single most important act of precision in the whole pipeline. In code, it's clean. We pass our allowed entities and relations as literals into SchemaLLMPathExtractor, then add the KG validation schema, a dictionary saying which relations are legal from which entity, so a drug can treat a disease but never has phase. Crucially, strict equals true, anything off schema gets dropped on the floor. That one flag is our noise control switch. Now we connect Neo4j and build. Neo4j property graph store opens the database. Then PropertyGraphIndex from documents runs the whole pipeline. It feeds our clinical trial documents through the SchemaGate writes the typed graph into Neo4j, and because we pass an embed model, it stores vectors right alongside the nodes. That embedding step is the mutual indexing from KAG, structure and source text, dual indexed. Let's see what we built. Inside Neo4j now sits a clean schema-typed property graph, drug nodes, disease nodes, trial nodes, wired by only the relations we allowed, every node carrying its properties and a link back to its source chunk. Half the lab done, but a pile of typed triples isn't yet a map. For broad questions, we still need structure on top. Now the second half, the part that makes this a complete GraphRAG index. We take the property graph we just wrote and run Leiden community detection over it, straight inside Neo4j using the GDS library. 2 moves: first project the graph into memory, then run the Leiden algorithm and write community ID back onto every node. Here's the community code in Cypher. First, gds.graph.project loads our typed entities and their relationships into an in-memory graph called clinical graph. Then gds.leiden.write runs the algorithm and writes a community ID onto each node. We ask for intermediate communities so we keep the full hierarchy, and it hands back the community count and the modularity score, our quality number Q made real. And here's the result animating in. Every node now wears a community color, the graph splits into tight clusters, and because we asked for intermediate communities, those clusters nest into levels. Find neighborhoods at level 0, broad themes higher up. The modularity score tells us how crisp the split is. That's the same hierarchy from earlier, now living inside our medical graph. One finishing touch turns clusters into a usable map. For each community, we gather its member nodes and ask the language model to write a short report, just once. Those pre-written summaries are the global summary map we talked about. Now broad questions read a handful of community reports instead of scanning the whole corpus. The index is complete schema-typed graph plus hierarchical communities plus reports. Let's zoom out on everything the lab produced. Documents flowed through the schema gate into a typed property graph in Neo4j. Leiden carved that graph into hierarchical communities, and the model pre-wrote 1 report per community. Both halves fully built. Notice we built the index but haven't queried it yet. Module 3 will show how to search these communities locally and globally. So how do you choose in your own project? If you need precise, auditable facts for a specific question, lean on triples and a strict schema. If you need themes and global summaries over a big corpus, lean on communities and reports. And honestly, in production you usually build both over one property graph, exactly like we just did, and let each question pick its lane. Quick recap of the superpowers you just earned. You can name the 2 construction paradigms and their trade-offs, tune the schema-free to schema-constrained dial, stand up a strict property graph schema in LlamaIndex and Neo4j, and create hierarchical Leiden communities with reports. That's a complete queryable GraphRAG index. Next module, we finally get to interrogate it.
If you like this video, please subscribe and share. Thank you.